Um, Hi, I'm Nils from Mainz. I think this was the first time today that I was introduced as a theory speaker, typically being an experimentalist. But that's fine, we'll make do. Yeah, so main purpose, from what I understand for this first lecture, is basically to introduce you all to K matrices in a way that it maybe removes a little bit the anxiety of going from, say, the simple one-channel Breit-Wigner case to more complicated but also more correct cases using K matrices, and kind of removing maybe a little bit this label that it's more complicated, because in many cases, theory remains fairly easy. And so main idea of the first lecture today is to kind of point that out. Right, so you should be hopefully seeing my iPad screen now.
Yeah, it's good. Yeah, works.
Perfect. Okay, so yeah, just to set the stage maybe a little bit, I thought it would be good to start here at the beginning. What we aim to describe is the scattering process, A plus B to C plus D. And we know from textbooks, from Fermi's golden rule, that in the center of mass frame, we can do that using this equation here, where say the differential cross section is given by some constants, this kinematic prefactors, and then some invariant amplitude squared. And so for the purpose of this lecture, we will assume we cannot calculate this invariant amplitude from first principles. So if this was QED, we'd just go ahead, calculate Feynman diagrams and obtain this matrix element. But in general, if we're discussing hadron physics, that's not an option that we have. We will also assume that either this case that I've sketched here are for spinless particles in an S-wave, or we will assume otherwise that we have already factorized this amplitude and then taken out everything that's angle dependent. And so what we're concerned about is solely the dynamics of this problem. And so the most common choice that people typically make is to set this invariant amplitude equal to Breit-Wigner, where that's just fine in the case that you have an isolated resonance in the single channel. You'll typically hear people in this introduction tell you that you cannot do that if you have multiple interfering resonances, because then adding these Breit-Wigners will violate unitarity. The other, and I think more practical, more important reason not to do this is that much of the interesting physics in recent years in hadron spectroscopy is happening close to threshold. So typically it has overlapping resonances and happens near thresholds. And so instead of boring you here with some, showing you some argon diagrams of two Breit-Wigners that violate unitarity, I thought it would be much nicer of an introduction if instead I showed you some data where it's very clear already from looking at the data that this approach will not work. And then we will work towards solving this using K matrices. Of course, that's now, I'll show two examples. That's, very personal choice in the sense that a different speaker would probably show you two different sets of data. So if your favorite example of coupled channel effect is not shown here, I apologize for that. Right, so first thing I want to show here is this J psi decay into phi and two pseudoscalar mesons. On the left-hand side, J psi to phi pi pi. Right-hand side, J psi to phi kk. And so the interesting feature that we're looking at is now this peak here. This is what's known as the F0980. And so the reason we're looking at this plot is because the intensity of this basically drops exactly to 0 here at threshold for 2 kaon production. So if we look into the 2 kaon channel, that's what's shown on the right-hand side here, we again find the F0980 that produces a signal that basically starts and rises vertically at the kaon threshold. And so this is very clearly a coupled channel effect where that particle decays to 2 pions up until the point where it reaches the kaon threshold, and then has much stronger coupling into the 2 kaon channel than it has into the 2 pion channel. And so the 2 pion channel, the intensity basically disappears instantaneously, and all the intensity goes into 2 kaons. And so very clearly, if you would, now go ahead and take a Breit-Wigner for the left plot, take a Breit-Wigner for the right plot, you would get out two very different particles, a very narrow one on the left-hand side, and a very broad one on the right-hand side. But you clearly wouldn't capture the essential physics in this problem. I want to show you a second example. That's a much more recent plot. That's this one from best 3. This is the ±2d bar. I'm showing this example because this is what I've most recently been working on. So again, very personal choice here. And so the reason to show this is, first of all, you see the data here. It's a very nice measurement, very detailed cross-section. That looks very hard to interpret. So you have lots of structure, much of that has very strong energy dependence, but it's not clearly peaking at any position. And so in particular, the region I want to highlight is on the one hand side here. So you see a broad peak happening at roughly this energy. This is threshold for d star, d bar. You see a second big structure happening in this plot. That's roughly here. And that's threshold for d star bar production. And so it turns out that if you look into the literature, there's an old paper by people in Cornell who are doing all these calculations of charmonium states from potential models. And so what they showed, or what they predicted, is essentially exactly the spectrum. And they predicted this extremely well, and in particular predicted that this peak on the left-hand side, so this one here, that that's not a resonance, but that is actually related to the fact that you can have the initial d plus e minus come in. And once you're above d star d threshold, you can have an additional process to produce d star d, and that's this process. To produce d bar. You have an intermediate d star d pair here now. And so they predicted, and it was 45 years ago, 45 years before the measurement of this cross section, that there would be exactly this structure at 3.9 GeV coming from this coupled channel effect. And so clearly interpreting this data then also requires some sort of coupled channel treatment. I hope that's motivation enough to spend the next 40 minutes or so with me talking about K-matrices, coupled channels, and how to treat these problems in a proper way. And so the main idea of what we will be doing today is to start from unitarity of the S matrix, construct a coupled channel amplitude, or construct an amplitude per se. It doesn't have to be coupled channels, in a way that from the beginning, by construction, we avoid the limitations that apply to sums of Breit-Wigner approaches. All right. So yeah, if unitarity is our main ingredient, we best start by writing that down. So unitarity of the S matrix here means we have S dagger S being equal to S dagger being equal to the unit matrix. And this just relates to conservation of probability. Now what we will be doing is we take out the non-interacting processes to define a transition operator. This is all just textbook stuff. So that looks like this. S is then equal to the non-interacting part. So that's just the unit matrix. This is the part that does nothing. And then depending on conventions, you will typically find IT or 2IT here, where T is now this transition operator that contains all the interesting physics that that we want to calculate, that we want to describe. You will sometimes find in the literature a different expression. I will list that here because we will also use this later, where instead of having this 1 plus 2IT, you find something like 1 plus 2I, and then square root of rho. This is a phase-based matrix. We'll come to that in a moment here. And then we call the invariant matrix element M instead of the transition matrix T. So we'll use this later, but for now we'll concentrate on the blue part. All right. Yeah, so as I said, main idea is to use unitarity. So we can now take this definition of the S matrix in terms of the transition operator, insert that back into the unitarity equation. And so what we get is SS dagger equal to 1. And then we now just insert. So that's 1 plus 2 IT times the dagger of this. We can multiply this out. That will give us this expression. Yeah, we can subtract the 1 on both sides, bring the TT dagger term onto the other side, divide by 2i, and then what we're left with is this expression. Oops, sorry. And so now we take this, multiply by the inverse of t from the left-hand side, multiply by the inverse of t dagger from the right-hand side. Then we're almost there. So this sets 2i1 equal to the inverse of t dagger minus the inverse of t. And now we bring one of the two inverses on the other side, split the 2i1 among the two sides, and arrive at the final line of this whole derivation here. So this will give us the inverse of t plus I times 1 equal to the inverse of t plus I times 1 and the dagger of this whole expression. So if we've now done this using, where's my pointer? It doesn't matter. So if we've done this using this green expression here instead, where we had the invariant matrix instead of the transition operator, we would have here arrived at the very similar equation where we have now the inverse of M. And instead of having a 1, we would have this phase-space matrix rho here, and would have on the other side the inverse of M, again, plus I rho, and the dagger of this. So nothing changes much whether we use this, the expression for the invariant amplitude or just the expression for the T matrix. All right, so I'll put a star here. We will reuse this equation later. Now the key part at this point is that we compare the left to the right-hand side. And what we find is that they're equal apart from the dagger on the right-hand side. And so we can now use this equation here to define our K matrix, or to be more precise, people used to define here as the inverse of K. And then the other side of this just becomes the inverse of K dagger. And so if that's the same, this matrix has to be Hermitian. If we, in addition, require that our physics is invariant under T symmetry, so the physics is the same for switching the initial and the final state, then that means this matrix K also has to be symmetric in channel space. And so if it's Hermitian and symmetric, then that means K here has to be a real valued symmetric matrix. And so that's really the key part of the lecture up until here. We've used unitarity of the S matrix to derive a new matrix that we call K that has to be real valued and symmetric. And so far, that's all we've done. I should take a moment here using this green equation and maybe highlight the fact that we have only defined here the inverse of K up to a real valued constant that we can add here on both sides. So if you put here plus some matrix R is real valued and diagonal, we can add that on both sides of this equation and still keep that consistent. So we've only defined K up to that real valued constant along the diagonal, or it doesn't have to be constant, a real valued function along the diagonal. We'll not talk further about this, but this is important for the second lecture by Misha later on, because this directly relates to the analytic properties then of this problem. All right. So let me write down. From this, it follows that K needs to be symmetric. And that means K is real valued. So this is not by choice of parameterization that K has to be real, but this is really required by unitarity. Okay, so we have two things left to do here for this to be of any practical use to us. A is we need to make a model for K. And B is we need to solve this for M, because this invariant matrix is specifically what we need and what we wanted to insert here into this expression for the cross section. So this is where the physics is. We need to solve for this invariant amplitude. And so the second step we will do first. This is where we come back to this equation that I started earlier. We can use this to solve first for the inverse of M. And that's just the inverse of K minus I rho. And then from here, we can take the inverse on both sides. This will give us a K to the power of -1 minus I rho. We have to inverse this. And now here as the final step, what we do is we take out the inverse of K either to the left or to the right. This will give us two expressions that are always used throughout the literature and should always be the same. So one option is to take K minus 1 out to the right. So this will give us 1 minus IK rho, the inverse of this, times the K on the right-hand side. But we could have also taken this out on the left-hand side and then get 1 minus I rho K, the inverse of that. There's a third option that is of less practical use than these two, but that should, if everything is strictly mathematics and then we don't do a fit where things are difficult to control, there's a third option that should also be identical, and that's if you take the K out to both sides. And so in principle, all of these equations should give you identical results. And so now all that's left to do is make a model for the K matrix. Before we do this, I'd like to highlight a little bit how to interpret this plot. How to interpret this equation, so in particular this one here. And how to interpret it is in this way, using this diagram here. Because what you can do is you can expand this in terms of a series. And if you would expand, just remove this real quick. So if you do a series expansion of this term, what you will get is something like this. And so on, which is just the mathematical description of what I put in terms of diagrams down here. So really what we're doing is we're describing addressed interaction in terms of multiple bare interactions. So we have our matrix K, and the matrix K sits here. It really describes the interaction coming from some initial channel I going to some final channel J, and then that matrix element would be this one. And this really describes just this pure naked interaction. Whereas the physical reality, what we observe, what we fit in the cross section, involves this infinite series, where, for example, we now have the second term here, which is just what I draw before in the motivation when it came to this DD bar cross section, where we now can have some initial channel here. Our final channel is going to be the same, but then in the intermediate system here, we can produce an additional pair of particles that rescatters. And so all the interactions are then summed over this infinite series. Okay, so when it comes to interpretation, that means this matrix M, also the matrix K and rho, these are matrices in channel space. So what M is describing the observed or dressed cross-section, so the one that we observe in the experiment. For channel I, scattering into channel J, we have the rho, where I still owe you the definition of this. This is really just what people typically just call the phase space. And so this is a diagonal matrix where we have the Kronecker delta, making sure there's no off-diagonal terms. And then this is really just the breakup momentum of the particle in channel, or the two particles in channel I in the center of mass frame divided by the center of mass energy. And so what's left then our K matrix itself, and this is really just the bare interaction between the particles. Okay, and so in the second half, let's look at some particular cases, how to construct this matrix K, how that behaves compared to, say, the Breit-Wigner that, of course, we would like to recover in the case of a single channel in a single resonance, and in case of two resonances that are far enough that we would call them isolated. We said before, the Breit-Wigner is the correct description in that. So we expect our K matrix description to recover those cases, but then to also produce these coupled channel effects that I showed earlier. So we'll have a look at a few examples now. And so the easiest example is we use a single channel with a single resonance. It's okay, just 1K, it's not a matrix anymore. We have a coupling constant that couples to this resonance. That coupling constant affects the initial state and the final state. Here the initial and the final state is the same because we have a single channel, so this becomes a G squared. And then we just divide this by the propagator of our resonance, which is just M squared minus S. And so we've really just made the most simple model possible for the bare interactions where we have the initial state coming in, coupling to a bare pole, and the initial state going back out. And so now what we do is we take this K matrix, which is just a number, not a matrix. We plug that into our equation for the invariant matrix element, which was this one minus IK rho inverse times K. We plug everything in. This will give us an I G squared times rho divided by M squared minus S to the power of -1. We multiply this by the K on the production side. Multiply everything out. And then what's left is basically what we expected. The G squared divided by M squared minus S minus I G squared rho. And so so this already looks a little bit like a Breit-Wigner, right? And so the only thing we have left to do is to identify G in terms of a Breit-Wigner width. So if we just set G equal to a new parameter, gamma times the mass, take the square root of this, just insert this into the equation above, then this reduces to exactly the relativistic Breit-Wigner with the energy dependent width. This energy dependent width just means that the width is the constant times rho, where rho depends on the energy. Yeah, so this gives us back exactly what we expected. That's good, because we knew the Breit-Wigner works in this particular case where we have single resonance, single channel, well isolated. So this is expected. It's really just confirming that this slightly more complicated K-matrix amplitude that we're constructing, that it falls back to the simple things in the simple cases. Okay. From here, let's just see what happens if we now use a single channel and two resonances. We make a new model for K. K is still no matrix, just a number here because we're still talking about single channel. So now we have first resonance that we'll call A. The coupling constant for that, again, same coupling constant for particles coming in and particles going back out, so GA squared. Just divided by the bare mass minus S again. And then we add second pole B. And that's all. And now we go ahead, insert that into this equation for M again, multiply everything out. I've now checked this before so that I don't have to do this in handwriting. And so what we get is this equation here. And so we can look at that a little bit further, because here it's not immediately clear what it is that we've gotten out, which is good, right? The same goes that adding two Breit-Wigners for the case of two resonances that are non-isolated but are in fact overlapping should be wrong, should violate unitarity. So we did not expect to get two Breit-Wigners back out here. So the fact that, at first glance, this is not two Breit-Wigners, that's good. I think during the first exercise, you will look at this case more closely. So we'll not look here at the specific case, where you have two overlapping resonances. But what I want to show you are the extreme cases of this problem now. And so the one extreme case that we can make is we set the pole mass to being the same for both poles. And so then what happens is that this thing here is 1. This is also 1. And so this just reduces again to a single Breit-Wigner. Where now the width of the single Breit-Wigner corresponds to the two couplings squared. And so this already shows us that even in the most extreme case, where the overlap is such that the two resonances sit at the exact same position, we now construct a single Breit-Wigner, which in itself conserves unitarity. So even in this most extreme of cases, we do not violate unitarity. The other extreme case is the one where we now expect this to reduce to two Breit-Wigners, namely the one where the two resonances are isolated, meaning that, say, the distance between these two bare poles moves to infinity. That would correspond to isolated resonances. And so now, I'll just remove this real quick. If we look at this expression here again, so if we're in the vicinity of resonance A, that means resonance B is infinitely far away, which means this expression here tends towards 0. And so the only thing that's left is the Breit-Wigner on the left-hand side. I tagged wrongly here, I see. This should be a B. And so the right-hand expression just completely goes away because that is infinitely far away. And so in the vicinity of resonance A, this reduces to a single Breit-Wigner. If we now go to the right-hand side expression, and we say we're in the vicinity of resonance B, then again, this thing here tends towards 0. And so again, this reduces to the other Breit-Wigner. And so this really shows us where the saying is coming from, that the Breit-Wigner works for isolated resonances, because that's exactly what we've constructed here. We move these two poles infinitely far away. This reduces to just to the sum of two Breit-Wigners. Okay, so those extreme cases work. Now let's look at the more interesting case where we actually have coupled channel effects, the two-channel one resonance case. And so here for matrix K, for now, I will just put what Remco had as the countdown before this started. So we don't fill the K matrix elements with any life yet, just insert it like this. That'll become clear in a second. This will just make our calculation a little bit more simple. So we now take our expression for the invariant matrix element, insert this K matrix and solve for M. And so what we get from the inverse of, we have a matrix that we need to invert. If I just go back maybe briefly here to this expression here. Now K is matrix valued, the 1 is a matrix, the unit matrix rho is matrix valued. So we actually need to invert a matrix here. This will give us a determinant, and so that's where this following number is coming from. We get 1 minus rho 1, rho 2 times the determinant of K minus I rho 1 first top corner element of the K matrix plus rho 2 the bottom right-hand corner of the K matrix and the inverse of this. And then that leaves the inverted matrix that we have to multiply by the right-hand side K. And that gives the following 2 by 2 matrix here. K11 minus I rho 2 determinant of K. In the top left-hand side corner, bottom right-hand side corner is then just K22 minus I rho 1. And again, the determinant of K. And then these two are unaffected. So that's our expression for M. And so if we now make a model for the elements of the K matrix, it will become clear why I've written this in this slightly weird way. Because if we now say we have two channels and a single resonance, then our elements of the K matrix are basically the same as before. We now have the coupling to the incoming channel. We have the coupling to the outgoing channel. So this is GI and GJ. Sorry if that's hard to distinguish. Divided by the mass of the resonance minus S. And so just from this, we immediately see that the determinant of K, which is G1 squared times G2 squared minus G1, G2 times G1, G2, that's 0. So the determinant of K vanishes, which is the main reason I've written the equation above in this weird way, because we can now enter a 0 everywhere, where we now have determinant of K. And so that gives us an actually very well-known expression, namely this one. We have 1 divided by M squared minus S minus I rho 1 times G1 squared plus rho 2 times G2 squared multiplied by the matrix of coupling constants. So that's G1 squared, G2 squared, G1, G2, G1, G2. And so this is what we all just know under the expression Flatte formula. It's nothing but the K matrix for a single resonance coupling to two channels. And so here I've now brought a plot of what that looks like. That's what's shown here on the left-hand side. This is particularly this case that I was showing before. We're now red here. This is pi pi to pi pi scattering. The blue here is pi pi to kk bar scattering. And so this is chosen in such a way that the bare pole here sits very close to k on threshold. The coupling constant is much larger for the k on channel. So G2 in this picture here is much larger than G1 by about a factor of 4.5 or so. And then what you get is very similar to the situation that I showed before. You get a very narrow resonance in the pi-on channel. You get this broad tail in the k on channel, the enhancement happening directly at threshold. You can make this even more similar to the data that I was showing before. If we allow this amplitude to interfere with some slow moving or non-resonant amplitude, then what we get is this. So here now, K11 is made a little bit more complicated, only very slightly. By adding some small constant here to interfere against. And then we also introduce, in addition, this effect that this now drops essentially vertically to 0 at the k on threshold. So by very simple means, we've just, plotted something that looks very similar to what I was showing earlier, motivated by actual experimental data of exactly these kinds of effects. Okay, so before we go to one more theoretical detail, let me give you one, or maybe the common general parameterization that people use for K-matrix analyses. And that's this, where an element of the matrix K is given by some sum over poles. That pole always couples to the final state, it couples to the initial state. Divided by this bare pole. So this is just the sum for bare poles. And then mostly in literature, you will find that you're allowed to add a polynomial in S here. So we have a sum over K, some polynomial that can be channel dependent. So just imagine this as some, say, non-resonant amplitude that leads you from the initial state J into the final state I in the scattering. And so this is can be a polynomial in the center of mass energy squared. You will often find this called background terms. That's not because that's physical background. This is supposed to be signal channel. So I think maybe a better name for this would be to call it non-resonant or contact terms. But again, it's nothing complicated. It's really just a polynomial in the center of mass energy squared. And so essentially, the main reason to have this additional ingredient is you might have resonances that are far outside the region that you're fitting to. So you can model the tail of that resonance by a polynomial, hopefully by just a constant term to not have too many parameters. You might have done some complicated T-channel exchange that you do not want to make a microscopic model for. And then also you would just plug in a polynomial and hope that any fit would use this freedom to describe the additional effects that you made no microscopic model for by this contact interruption. Okay, so I should have about 5 minutes left. That means we can talk briefly about applying this K-matrix formalism not to 2-to-2 scattering. So right now, everything we've done was two bodies coming in, two bodies going out. But I guess for many people applying this, more interesting case is the decay of one particle into three particles. And so the general idea here goes back to Hüsken. And it's thus called Hüsken's p-vector formalism. And so my derivation of this might differ a little bit from what you find in most textbooks or articles. But just bear with me here. I promise we get to the 1-to-3 case. So far what we've done was always just to describe the scattering process, right? Going from the initial to the final state. We've learned now that the matrix element for this is essentially the sum running over K, 1 minus IK rho, the inverse of this. And now we are interested in the final state side of this. We sum over the intermediate channel K and then have on the initial side here, our initial state, and that produces an intermediate pair of particles with index K. Now to get to the p-vector formalism, the most simple way possible, the only thing we need to do is realize that we can fix the initial state here. We run an experiment where that initial state is always the same, doesn't matter which one. What that means is that this right-hand side, K, Ki, that's just a vector. So we can use this to define the p-vector with index K, just this element of the K-matrix. And then in principle, you're basically done. This is the easiest way to derive the p-vector formalism. You replace this right-hand side matrix K by just a vector, realizing that your initial state isn't changing. Now what people typically do, so why this is not the end of the story, is you make the claim that your coupling to the initial state is small. This again does not necessarily strictly have to relate to 1-to-3 scattering yet. This is also 2-to-2 if you want. So let's say require the coupling to the initial state is small. Then what we can do is we can remove this initial state from the K-matrix. We can remove it from the rho matrix and thereby basically remove it from this denominator up here. To remove the initial state from this expression. So if you have a matrix in channel space and including your initial state, that is, I don't know, a 4x4 matrix, then you reduce this denominator to a 3x3 matrix. And then we get what's now called the F vector, and typically in this E vector formalism, that's basically the same thing we had before. We sum over K, 1 minus IK, and I now put a tilde here just to indicate that we have removed the initial state. So this matrix, or these matrices are one lower in number of dimensions as the K matrix that we had put before. We sum over the intermediate state K, and have the production vector on the right-hand side. And now this is textbook Hüsken's p-vector formalism. And so this is motivated, just move this up here. This is motivated, again, essentially by this plot that I was showing before, because what we're constructing is this infinite sum. And what we've now done is basically perturbation theory. Right, because of this element of K here on the left-hand side, this becomes just PK instead of being an element, because we always keep the initial state the same. And now we've removed the initial state in this rescattering loop. And so what we've done is we have removed terms that would be quadratic in the initial state coupling. So if that initial state is small, we say that that goes to 0. And we've removed essentially these terms. So that's the only additional assumption that goes into this p-vector formalism. And so the main application of this is 1 to 3 decays. So let me just give a concrete example here. Could be the radiative J psi decays. We have the J psi coming in, decays. We have a photon coming back out, plus a pair of pions. And all you really do now is to turn around this diagram and interpret it as this diagram, where you have a J psi and the photon coming in, have the 2 pions going out. Now this is again 2 to 2. And we can make a very good argument that a resonance in the 2 pion system at say 1.5 GeV or so has very small coupling for radiative decay into the J psi at 3 GeV. And so this is exactly where that idea comes from. And so this allows you to describe now the dynamics in the pi-pi system. We stay in this picture by this F vector in the pi-pi final state, summing over the possible intermediate systems, 1 minus I K rho, where the left-hand side index here would always be pi-pi, and times the p vector. And so this sum here, this would now run over pi-pi, but will also run over kk, eta, eta, and so on, depending on how complicated you want your coupled channel problem to be. And so if okay, we're like 3 minutes over time. If I can get like 30 more seconds, let me maybe just say that this is one of the key features of the K-matrix formalism, or in general, this p-vector formalism, is that one can make now the case that this part here, that's universal. So the idea of this p-vector formalism is we can determine this elsewhere. So if someone has a huge high statistics data set of pi-pi to pi-pi, pi-pi to kk scattering, we can determine all the physics of these processes, put that in here, and then have fit parameters only in our production vector to describe J psi to gamma pi-pi, for example. Okay, this would be all I wanted to get to in this time slot, and I think then there's plenty more coming than from Misha and then during the examples. Thanks.